mentors of the team joining us and introducing themselves as well as the team. We probably will also have some external audience. Uh, Welcome and thank you for taking your time and participate in this final presentation. This is a challenging time for many of us, especially for our students. But I'm glad that our students in EC 191 all survived. Not only survived, they also did a great job finishing many non-trivial milestones in each of the projects. In the later presentation, you will see that they are really making a lot of interesting technical achievements, software, hardware, machine learning algorithms, etc., through various ECE 191 projects. So today our presentation will go through team A, B, C, D, E, and for each presentation, we will ask the mentor to introduce themselves and introduce the team as well. This will take about 2 to 3 minutes. Then each team will take 15 to 18 minutes presenting their project. During the presentation, any of the audience can raise questions at any time. We hope all the questions and answers can be kept brief so that for each team, the total time of the presentation will be about 25 minutes. So we already had the rehearsal for all the teams last week, so hope everything will go through smoothly. If you have any private questions, feel free to ask me through the chat on Zoom. Okay, without further ado, let's start with Team A. And the mentor is Dr. Jules Jaffe from UCSD.
Okay, so can you guys hear me? Am I coming through? Okay, cool. Well, so my group is down at Scripps Oceanography, and our goal is to develop new sensor systems for understanding, measuring the ecology of the ocean. And that includes a small robots that we developed, listening and also seeing in the kelp forests right near La Jolla. We have a project there. And then the project that these great students undertook this quarter was to help me with some advanced methods to allow us to improve our capabilities for identifying organisms. We have a couple of microscopes on the Scripps Pier. You're more than welcome to go there anytime. I could try to do a screen share, but we'll pass on that. So spc.ucsd.edu has a real-time feed. We now have 2 billion images over the last 5 years of organisms that range in size from probably around 5 millimeters to smaller. Our resolution is probably 5 to 7 microns. So we can see guys that are around 30 microns with a reasonable amount of identification. And we're working with Professor Vasconcelos in ECE. We have an NSF grant funded to look at the use of deep learning for classification. We've been working with a lot of taxonomists. And honestly, we could do better. And so one of the ideas I had was a lot of the organisms look pretty much similar from certain orientations. And so the idea was if we had more than one image, could we in fact improve our capability to classify these organisms? And so I thought that would be a fun project for the 191 guys. We had a group last quarter that we had a great time with under Professor Kosman. And those guys had a bunch of friends and they said, hey, our friends would like to do something on deep learning. And I thought, well, hey, I could think of something. So we thought of this. And I've been impressed with their productivity. And you will hear more about that in the next 20 minutes or so. So thank you very much, Professor Zhang. And I see Varun is ready. The The members of the group are Kevin Youssef, Varun Malik, Yazid Al-Numay, and Yejun Lee, and I apologize for my lack of any of those languages. I'm not very quad or quantilingual, but they're all great students, and I'm glad we have them with us. So I guess we're going to turn it over to Varun now. Is that correct, Professor
Yes.
Zhang?
Yes.
Okay, I'll
great.
mute myself.
Thank you very much.
Professor, the host sharing is disabled.
Can you try now?
Yeah. Can you guys see my screen?
Yes. Okay.
Perfect.
Just a reminder, before every group's presentation, please introduce yourself, each of you, to us.
Yes, yes. Thank you for the introduction, Dr. Jess. We're Team A. I'm Varun Malik.
Kevin Youssef.
Yejun Lee.
And first, I'll start with the introduction, the overview of the project. So the big question is, why do we care about planktons at all? It actually turns out they're very important, and studying them can tell us a lot about the environmental changes from observing their composition, as well as they are a significant producer of oxygen. So studying and researching planktons is very important. In order to research planktons, we need to first identify the different species of planktons that there are. And it turns out there are well over 100 species of planktons. So in order to understand and then classify these planktons, there have been current technologies being used where there is a underwater microscope that takes pictures of planktons, and then using machine learning algorithms, we can then classify them. But traditionally, this approach has been just one camera underwater that takes pictures. So it's a single view approach. Now, the big question was, instead, if we use two cameras to take pictures of these planktons, so we would have pictures from two different angles, hence the multi-view approach. Will that yield a higher classification accuracy? So the goals of our projects were to get 3D models and extract 2D projections from them, so both for single view and multi-view data. And then we found a research online, past research, that did a multi-view classification. So we took their work and we tuned it to our project, specifically to classify planktons. And then after running our generated data into the tuned CNN, we then compared the multi-view accuracy to single view accuracy and see for which data set, which approach is better. So first, we constructed a multi-view classifier and tuned it to our project. Second, we created the 3D models. We got 3D models from a team in France, but we had to change these 3D models of planktons to adopt them so that they're more realistic and do a lot of processing on them so we can actually extract 2D views from these 3D images. So we did this both for single view data and also for multi-view data. And then we repeated the process for 6 different models. And we analyzed the results. So here, as you can see, after extracting the single view and multi-view data, we ran it through the single view CNN and the multi-view CNN to obtain results and then compare them. And the CNN, of course, was adopted to fit our data, so it was trained for each data set, each of the 6 data sets. Since we're all in different parts of the world, we use Microsoft Azure to collaborate remotely. It also has a really strong platform to work with CNNs with strong GPUs. So the running time was significantly reduced as opposed to if we ran the CNN and trained it on our local machines. Additional benefit is that it comes pre-configured with PyTorch or TensorFlow. So it was really simple to get this running and set up. Next, we'll talk about machine learning primer, which will be Yas.
Thank you, Varun. So we figured that maybe not all of our audience is familiar with machine learning. So we decided to include a quick primer of what machine learning is, what we're trying to do here. So at a very basic level, what machine learning is trying to do is they give it a certain input and try to classify it. It's best learned by example. The most basic example is linear regression. If you have pairs of two things, for example, if you have GDP per capita and the quality of life index for our country, those two are obviously related. And we want to know if you can, for example, find what the quality of life is based on what the GDP per capita is. And so you would apply a linear regression, which is what you usually do in Excel to find out what the output should be. Basic machine learning model. Another example would be image recognition, which is what our team is doing. Speech recognition, which is what team E is doing. There's a variety of examples. One of the more weird and interesting one is search engines. You give it keywords, and based on that, it would search through the entire web and give you the links that are most relevant to what you're searching, which uses machine learning algorithms as well. So the ones that are most relevant to us are probably SVM and CNNs. SVMs are support vector machines. What they do at a very basic level is that given two sets of data, like on the far left image, this one has 2 dimensions. And what we try to find is a linear function that separates the two. So based on the value of the function, if it's above a certain value, you classify as a class A. If it's below, classify as class B. And this applies to multiple classes. Sometimes you get data that's not linearly separable, so you apply a kernel that transforms it into data that you can separate. This is considered a complex optimization problem, so we have techniques to find the optimal solution. But what we're applying to our project is a convolutional neural network, which has 2 parts. First part is a series of convolutions, which is a series of functions that looks at the neighbors of a pixel to get new values, and you apply a series of those to get what we call a feature map. Our human eye doesn't really understand that, but it's perfect for a neural network and what it does. So a neural network has a series of layers. Each of them has weights, and you multiply those weights. Based on the value you get in the end, you classify. This is a very hard to optimize function since you have multiple weights. And so we rely on architectures that are set before. The one we're using is just ResNet 18, which has 18 hidden layers. So this is the structure of our neural network. So we get 2 images, 2 views of the plankton. Each of those go individually, through a single view CNN. Then we pull those results together and we put it through the last CNN, which looks at the results of the first 2. And based on that, it would decide what type of plankton it's looking at. So that concludes our machine learning primer. Now we're going to talk about how we created our data set. So we leveraged our connections to obtain 3D models of plankton from a research group in France. We got 7 models. Those are STL files, which are made from millions of triangles. Those are the models here. And what we're trying to do is make projections of those models to input into our CNN. So what we did was we took those models, we put them into MATLAB. And the first thing we did was we added the texture to it, so it's not just a bunch of dots and looks weird. We also put lighting so that it looks realistic, what a microscope would look like. And probably the more interesting part was that we needed to find the correct camera angle, but we had a lot of degrees of freedom there. Those would be shown next. So the camera angle, we have 3 degrees of freedom from choosing on our plankton. We have a pan, which is similar to a polar angle, your theta. We have a tilt, which is your azimuth angle, your phi, and a spherical coordinate system. You also have a roll. So what we did initially was that we made those angles uniform. So it's equally likely to be anything between negative pi and pi, for example. And yeah, what we found was that that doesn't work. What we found was that there's a very dense distribution on the north and south poles. And so what we needed to do was to modify our phi, our azimuth angle, so that we counteract that. This is based on the transformation equations. This is the distribution we found. where you use a uniform distribution between 0 and 1. So in the picture on the left is the one with the uniform distributions. The issue here is that if phi is close to the north or south poles, changing your theta, your polar angle, doesn't change your location by much. And so you have a dense concentration around there. But once we apply the transformation to our phi, we get an equal distribution of angles, which is what realistically you would get if you just put a microscope in the ocean and take random pictures of planktons.
Okay, so now we're going to talk about the 6 different data sets that we created. The first data set that we created was a simple one where we just had the plankton in the view. So for single view, we looped over 1,000 iterations, each one randomizing the camera position as Yas mentioned, and then saving the image. For 2 view, we also looped over 1,000, took the image and then turned the camera 90 degrees to get the side view as well. And then those pair would go into the 2 view CNN. Here you can see an example of the simple view data. As you can see, not much is going on, and CNN could easily classify these types of images. Next, we wanted to tackle the issue of added noise from our hardware, namely the underwater microscope. So we simulated this by adding some blur to our images. So before saving our image, we call on a function that basically blurs the image using a low pass filter. As you can see in this data set, the images are a little more complex. A human can easily still classify them, but a CNN would have a harder time. In this data set, the silhouette data set, we wanted to take out all the data other than just the feature that is the shape to see if that would have a different effect on the CNN. So here, before saving our image, we binarized the image, which basically means taking an RBG image and then making it into a binary black and white image. And then you can see in these examples that the only information being conveyed is just the shape of the plankton. After that, we wanted to tackle the issue of that the planktons are actually not all the same size due to different mutations and different growth stages. So to simulate this distribution of sizes, we would randomly scale the object size right before taking the image. In these examples, you can see the one on the left is a larger iteration than the one on the right. These are only 2 examples, but in the real data set, it was an entire distribution for each data set. After that, we wanted to simulate the problem where particles and other organisms would be in the same picture. We did this by including spheres into the scene. We randomized the sphere in terms of the number of the spheres, the size of the spheres, and the positions of the spheres before taking the images. And in this data set, you can see how this adds more complexity to the image. There are more objects, and in some specific views, these objects would overlap with our plankton of interest and would alter the shape of the plankton. Next, we wanted to take it a step even
it has never been a successful app out in the market.
By adding 2 new shapes into the image, other than the sphere, which was an ellipsoid and a rounded cube. In this one, we still randomized the number of the objects, the size of the objects, and the position of the object, but we also added a randomized angular orientation to the objects. And in this data set, you can clearly see it's a lot more complex. The plankton is definitely overlapped with the other objects, and it would be much more difficult for CNN to classify these data sets. Next, we'll go over to Eugene to talk about our results.
quickly recap what Kevin just said. The simple data set is the one we added tester. It's more realistic to what we're getting from the microscope. Unfortunately, the first challenge we see is the both result from single view and multi-view. They're pretty similar. So we quickly generate four other data set to see what's the difference. By looking at the silhouette, which is a binary file on the third column, we can see just by the general shape, the CNNs from both model can quickly identify what kind of plankton we're looking at. So also as the suggestion from our mentor, we changed the size of the plankton to represent the various size distribution in the real images. Also, we observe that they're actually causing a small job to the performance. Later on, we're thinking maybe we'll add a little more complexity to the image. Will help better understanding the strengths of CNN. So we create the block one. So for the block one, as we can see with the level, the degree of the clutters happening, the multi-view CNNs start to stabilize around 96%, while single view will have a bigger effect by this kind of complexity. And now we can look the performance. For the last one, as we can see, single view has a hard time to distinguish Alexandron, which is a sphere. Because one of our clutter we generate also sphere, especially we also have ellipsoid in there. So that might create the difficulty for it to classify. So multi-view is doing a good job to help to improve these classification. So in general, we discovered, given our data set, for the normal, the simple image, we cannot
there has never been a successful app out in the market
outperforming single
for a period of 3 seconds, and that will indicate.
But when we are giving a clutter, so with noise and the clutters, these kind of variation, the random adding the complexity, single view CNN is slightly better than multi-view CNN. Sorry, is slightly better than single view CNN by a 3 to 6% margin. In our case, we do also realize these things might not applicable when this thing goes to hundreds and thousands species, and we need more training on that. But we conclude our result. At the moment, our project is now given a suggestion for the multi-view camera with the added expenses. Also worth notice, as multi-view CNN contains more layers, the training time will be much longer than single view. Now I open to questions.
Great, thank you very much, Team A. Although we are not physically present here, let us all give Team A big applaud, virtual applaud from Zoom. Thank you. Any questions from the audience?
Yeah, I do have a question. This is Jack Subham. Any particular reason why you didn't take advantage of the GPU cluster at UCSD versus going out and finding a service provider? So we have a nice setup at UCSD that's free of use.
So are you referring to, can we go back to the slide that was showing the result?
No, not the results. I'm talking about like you chose to go on a platform that web-based, and you have to pay somebody to use that versus using like resources that are already available at UCSD. So I don't know if you were aware. I'm guessing the question is that were you aware that we have a GPU cluster that students can use?
That's actually an interesting question. So after we're doing that, we also consult our mentor about this. So he's saying that on certain situation in a biological lab, that researcher looking at these organisms under a microscope, there's some clutter underneath that, then it's very difficult to recognize the shape. That's one also this thing, because after we looking at the binary files, so if the CNN can quickly figure out what's the image by looking at the shape, we're just thinking that was giving an intuition for us to change the segmentation of the shape, so that will add a complexity to the CNN. to classify the correct category. I'm not sure, is that answering your question?
That's okay, I don't want to take too much time. All right, so thank you.
So one comment, if you go back a slide, to the results, the bar graph where you had the, yeah, right there. So, I mean, the proviso on this is that as organisms get smaller, they all start to look more like spheres. So the most interesting result to me is the first one, the Alexandrium, because it did seem like in the multi-view it was doing much better. And these larger organisms, as they have more morphological diversity, it's really pretty easy to tell them apart. And it turns out in the ocean, the abundance of organisms goes up exponentially as they get smaller and smaller and smaller. So I was pleased to see that, you remember there was actually a bloom, a plankton bloom last month where we had the nice bioluminescence. And those organisms all look like brown spheres. But if you look at them from certain angles, they do have some distinguishing characteristics. So I wouldn't totally throw out the multi-view idea, because it seems like in that case it really did make a difference. But I also wanted to congratulate the team. I think they did an amazing job, and it was really a pleasure working with them. So thank you very much.
Great.
Thank you.
Any
Thank
other
you,
questions?
Yeah, any other questions?
Okay, if not, we will move on to Team B. Thank you again for Team A for your presentation. Okay, the mentor for Team B is Dr. Yiwu Tang. I think Yiwu is also here, right?
Yeah, I'm here. Can you hear me?
Great. Yes, I can hear you. Could you introduce yourself and the team as well?
My name is Yiwu. I work at Qualcomm RF and the millimeter wave transceiver IC design group. The project of the title of this project is cryptography, encryption and decryption using FPGA. So cryptography has very wide application in electronic transactions and digital concurrency, computer password, and wireline and wireless communications. In cryptography, a cipher is a pair of algorithms that use to encrypt and decrypt the plain text so that the communication is secure. The key generation is very important to make the cryptography security, efficiency, and integrity. And there are different ways to do the cryptography. In the software approach, is just by the coding, and in the hardware, it could be custom IC design. And FPGA is somewhere in between. It has the advantage of efficient hardware implementation and also the flexibility of the software program. It can achieve the high performance by the hardware implementation, but also has the flexibility to do the security updates in case there's a security system was compromised. So this project has a very broad skill set required. It covers the concept of cryptography, the algorithm, and the team member also implemented first with Python using software as a baseline. And then on top of that, they implement the FPGA with VHDL code. And using the software-based algorithm, they can cross-check their FPGA implementation. So they also learned, get familiar with VHDL code and how the FPGA evaluation board, the development kit, how it works. So the team member for this project is Catherine Yu. and Royal Kim, Jack Bay, and Brittany Wayne. And they did work in both algorithm, software, and hardware. I hope we get to know how it works in FPGA for the cryptography in their presentation. Thank you.
Great. Thank you, Yivu. Now Team B, it's your time.
Thank you for introducing us. So to go over just like more briefly of what our project is, on cryptography to develop the secure way to transmit any confidential information, and has many applications, especially in our social world and how everything's being shifted online right now. So it can solve the problem of personal information being accessed or corrupted by any adversaries or intruders. So we will present a hardware implementation of a cryptographic algorithm called Rivas Cipher 4, which we'll be calling RC4, onto the Nexus A7 board. Throughout the project, we verified our results with Python and a hardware implementation with the board.
So our project was sponsored by Qualcomm, which is a company that specializes in wireless technology. And our mentor was interested in this project because cryptography is widely used for securing communication. Our project focuses on implementing a simpler cipher called RC4, and it's not widely used today because of its weaknesses. But the reason why we chose this is because our entire team from the beginning was unfamiliar with HDL. And also some of the concepts in the simpler cipher can be used to understand how to implement more complex ciphers. And those concepts include pseudo-random key generation, using a key, encrypting, decrypting, partitioning bits, and implementing an algorithm on an FPGA. Next. So here are our project goals. Our primary goals were to implement pseudo-random key generation and encryption and decryption on an FPGA. And our stretch goals were to optimize the algorithm on the FPGA and do performance analysis. Next. And here is our approach method. Our first step was we compared different ciphers and chose one that we could implement in our time frame. And second was software implementation. So we implemented the RC4 in Python to make sure that we understood all the steps and we were getting the correct outputs. And step 3 was transferring that Python design into VHDL. And finally, step 4 was connecting that algorithm up to the switches and 7-segment display on our Nexus A7 board. Next.
So this diagram here is showing a brief overview of our system. So we internally generate our signals. So the main signals we generate are the reset, start, key, plaintext, and our plaintext. So from this, we move on to our main module. So this is our unit we designed. So it incorporates 2 memories, so one for the S box and one for the K box. So this one stores on the key. And the first algorithm we go into is the key scheduling algorithm. So this is abbreviated as KSA. So here we increment a counter from 0 to 255, and this generates our schedule of our key. Following that, we send the output into a pseudo random number generator, and this will randomize our numbers. Here it does a shuffling of S box, and it generates our key string. So this will be our secret key that we use. Following that, we do an XOR with our plaintext and our generated key string, and this will produce our ciphertext. And to get the decrypt of the text, we do the ciphertext with the key string, and that will generate our decrypted text. So with this data, we have stored it into a binary standard vector, standard logic vector, and we output it into an hex or ASIC character representation. And this will be shown onto the FPGA when we display it onto the 7 segments. Next slide, we have, this is like our design overview of how we proceeded. So first we had an initial design, and this we designed with a state machine to implement our process. Following that, we coded it into VHDL using a behavioral method, and we verified it with a simulation. So we had to check for a correct cipher, key, and generated key stream. Following that, we had to develop a synthesizable code. So this included, we had to reprogram our design to be synthesizable, and we also verified with our simulation to see if it matched behavioral and also Python implementation. From this, we implemented our FPGA flow, where we were able to place and route our hardware. And from this, we were able to program an FPGA by generating a bit stream that we then programmed onto our actual hardware. And we verified it with our hardware displays. So this was using our switches to toggle our 7 segments.
So I can go over with the encryption algorithm. So secure file transfer protocols like SFTP and HTTPS implemented cryptographic algorithms to encrypt any data transfer, such as advanced encryption standard called AES or data encryption standard DES, which are symmetric key ciphers. These symmetric key ciphers can be classified in 2 groups, such as like stream ciphers and block ciphers. Stream cipher is an encryption algorithm that encrypts 1 bit or byte of plain text at a time, such as RC4, Salsa, and Panama. While a block cipher takes a block of plain text and generates a block of ciphertext in the same size, such as AES and DES. Next slide, please. So we researched the encryption algorithm like AES and RC4. Then we narrowed them down to RC4. RC4 was designed by Ron Rivest of RSA Security back in 1987. And it was most popular stream cipher used in encryption protocols and standards such as WEP in 1997 and WPA in 2004 for wireless card, and SSL in 1995 and its successor TLS in 1999. So even though RC4 has a proven drawbacks such as not being very secure, cracked, and even deprecated, we proceeded with RC4 is because much simpler and faster in comparison to block ciphers for both software and hardware implementations. Next slide, please. So RC4 algorithm consists of 2 stages like key generation algorithm and pseudo-random number generator algorithms. So key scheduling algorithm uses key lengths from 1 to 256 bytes. That is used to initialize a 256 byte long table that is called array S, S-box, or substitution box. After our secret key pass into key scheduling algorithm, it performs permutations of the value in S-box that is implemented as memory, array of registers that serve the function of a lookup table. Next slide. So pseudo-random number generation can be achieved by first passing the seed key as an input into the key scheduling algorithm where the S-box is created. Then S-box will be passed into the pseudo-random generator algorithms. To further randomize the data, contents in the S-box are shuffled. So the key stream can be generated by looking up contents index by the sum of the SI and SJ in the S-box. Next slide, please. So here's how encryption and decryption works. For encryption, our secret key get into RC4 block. Again, RC4 block has 2 stages like key generation algorithm and pseudo-random number generation algorithm. RC4 block generate a pseudo-random stream, which is called a key stream. Then the key stream combined with the plain text using bitwise XOR to produce a ciphertext. Decryption is performed in the same way. Next slide.
So the challenges we faced were our initial design. From the hardware perspective, there is a difference in behavior of signals and variables, and how we have multi-threaded versus sequential execution, which is different for what we wanted to do, such as like running for simulation design or creating an actual synthesizable design. For hardware programming, for the synthesis phase, we experienced the error of nested clock statements not being supported. So we had to go back and convert all of our initial for loops we had written to if statements, since that was more of a synthesizable code for us. Then another challenge was to integrate the switch to trigger the displays with our state machine we wrote.
A very useful tool for helping us solve those challenges was simulation. So as you can see on the picture to the right, simulation allows us to see our inputs and outputs in text form. And we can use simulation to see our outputs without having the board physically, which is very helpful for us because only one person has the board physically right now. And in simulation, we can also report our intermediate signals and variables that we're using and detect switch changes and how our data is moving through the state machine. Next. So here are our states in the state machine. First is our idle state, which is where we're waiting for switch inputs. And depending on the switch input, we will switch to a different state. The SINT, which is the initializer state, the KSA, which is the key scheduling algorithm state, the PRGA, which is the pseudo-random number generator algorithm state, and the cipher and decrypt states are all the states that are used to go through the steps of the RC4 algorithm and compute the encryption and decryption text. And finally, we have our show text, which is where we convert our binary output into hex or ASCII and display it on our board.
So this block diagram shows our key scheduling algorithm. So it shows our up counter. We do it from 0 to 255. Following that, we have a storage box. So this is where we have our scheduled arrays. So I just want to point out that we store our key, our initial key, so our seed key, into an array. And this will be stored in bits, in bytes. So this will be 8 bits per character. And this is our basic overview of our key scheduling algorithm. And on the next slide, we show our block diagram for our pseudo random number generator. This also has an up counter where we use the same storage box where we also shuffle it. So we do a swapping in this one. And following that, through this pseudo random key generator, we generate our key stream. So this will be when we append our SBox elements into a stream of keys. So this will be a streamed binary array. And on the next slide, we show our results. So this is our results from all 3 implementations. So starting with our Python implementation, we use the same key and plaintext pair for all 3 methods for Python, PHDL, and FPGA. And we show that we have correctly deciphered their initial ciphertext. And we show that it was matching in all 3 implementations. And we also observed that our decrypted text is matching our initial plaintext. So this is an XOR of our cipher with our generated key stream. And so this verifies our successful implementation of the generated key stream as well as the ciphered algorithm. And here we show our performance analysis. So we can analyze the resource usage report after our simulation, and it can show us our number of registers we used as well as the number of lookup tables. And from these 2 values, we can calculate the error by the multiplication of them. And we can also see our clock, so with our maximum frequency being 100 megahertz. And this is just a general performance we have observed through the software. And it shows that we've really used a small portion of the available resources on our FPGA.
So here is the Python implemented result. We internally generate our secret key as group B and plain text as our names. As a result, the decrypted plain text show that the initial plain text has been successfully recovered. So next slide. And here is the VHDL implemented result. We preset both our secret key and plain text in binary numbers as an input. For displaying purpose, we convert all those binary numbers to hexadecimal so that we made them more readable. As a result, our plain text and decrypted plain text show that same output in hexadecimal. Besides, the result from the VHDL module match identically with the Python implemented result. Next slide.
And then now we're going to show you of the results on the actual FPGA nest. So here's a video of how switch 0 through switch 4 will trigger our key. Well, switch 0 is our key, switch 1 will hold our plain text, switch 2 our cipher text, switch 3 is our decrypted text, and then switch 4 is to control scrolling to display more than just 8 bits at a time. To show that more in detail, we can see how this would trigger this message, which is our key. And then we had our message as our names, Jack, Roy, Britt, and Kat. But because we wanted to display along the message, we had to create a scrolling switch, and that was what we used for switch 4. Same as here, this is our ciphertext, and continuing to the rest of the message is triggered by this switch 4 to trigger that. And then after the cipher, we are able to decrypt it, which our results are the same as our original plain text. So that was our results. And for our project impacts, FPGAs are more economical solutions for developing initial designs and prototyping and demonstrating a proof of concept for hardware applications. It allows hardware reconfigurability to be defined by the software. So for us, we were able to use the Vado design suite. And for social impacts, this digital data with this could potentially be used is to secure communications, electronic transactions, and authentication.
So for our goal assessment, the goals that we have met through this project is that we have successfully generated our key generation. So this was through the RC4 of the key scheduling algorithm, as well as implementing the pseudo-random number generator algorithm. And we also showed successful encryption and decryption of using our keys and our plaintext. So we also showed a brief performance analysis, which was identified as our stretch goals. And the goals that we have not met in this project frame is optimization. So we had some obstacles in our synthesis process, and this result in a few setbacks. In the next slide, we show accomplishments that we have made. So we did learn cryptography. We've observed acceptable standards that are widely used and different cipher algorithms. And we also showed a quick implementation using Python. So this was to use as our initial baseline for our verification method. Following that, we did a VHDL implementation where we designed a simulatable code using behavioral. And we also had to program it into the FPGA to make it synthesizable. So in this process, we showed it was successfully synthesizable, and we proceeded on with FPGA flow, where we did the timing constraints and we did the hardware route and placement for wiring. And we also have showed the hardware indicator and control successful message on our FPGA demo. And this concludes our presentation, and we are open for any questions.
Great. Thank you, Team B, for your great presentation. This project is one of the demonstrations of our students' learning capability, starting from scratch, learning to code in Python and the well-known challenging VHDL programming language. Everything works smoothly eventually. Great. Any questions from the audience?
Yeah, this is Jack Silverman again. What's next? What's the next steps? We're going to be doing something after you.
There wasn't a planned continuation to the project. Does our mentor have any words for that?
I know this lady, Brittany, that I think she's going to graduate school. I'm sure she's going to be looking for a thesis team.
So for the next step, they could go further from this stream cipher to more complicated block cipher, which is used in the current modern cryptography algorithm. It's more complicated, probably go beyond the scope of this project, but that could be their next step if they're interested.
I have one brief question for Team B about the resource utilization. Have you established a goal, quantitative goal? You mentioned that the resource utilization on FPGA is quite small, but do you have a benchmark? How small is considered small enough?
Because
go ahead, Roy.
So because our key and our plaintext that we used were small valued, so we didn't use very large arrays. So we weren't very concerned with the performance. We just showed the measure of our area usage using the register and LUT count to show the printing onto the FPGA as a bench score mark. But in terms of comparing it with data, since this is a stream cipher, it was a little hard to find some performances that show that it is very good or very bad.
Yeah, we don't have any other projects to compare our results against.
I see. So understand that you didn't have time to do the performance optimization, but in future, what do you think about the possible aspects that people can work on to further optimize the performance? Should they make the algorithm more efficient, or should they fine-tune the VHDL code so that it is further optimized in terms of the resource utilization on FPGA?
I would say the VHDL code, because actually as we were synthesizing our code, we saw that there were some latches that were generated, and usually those are not something that should be generated because they don't follow the clock. And if you want it to follow exactly what speed you want, then you should be writing your code in a way that doesn't generate the latches. And we weren't able to fix that because we didn't reach to the optimization.
Got it. That's a very nice observation. Okay, thank you, Team B, for your presentation. Now let's go on to Team C. So for Team C, the mentors are John Roundtree and Charles Tucker from PRA. I think Chuck, you are here, right?
And I'm John Roundtree from Popular Rotorcraft Association, a nonprofit charity that was started as a commercial venture from Dr. Benson, who created the gyrocopter back in the 50s. Okay. Today, to pretty much create safety devices. All right. I came to this late in life. I had retired at age 39 in 1990 after selling the world my software, the middle America corporate world my software for an accounting package. And an accountant, I wrote it to save my investment. It was one of the first mini computers 10 years before micros came out. Anyway, I got into this to help them because they were really struggling for a purpose. Okay, and membership was down and they weren't going to last very long. And now we've turned that all around, so much so that we are sponsoring 12 projects with 5 colleges for safety devices or for new modern improvements that also are safety devices. Hence, we have turned to you for the electronic portions of these. Some of them are like jump takeoff, where a gyroplane takes off it has a little propeller in the back, helicopter blades on the top. We can fly 90% of a helicopter's mission with 10% of the cost. We just can't hover and take off vertically. Well, now we've got a college working on taking off vertically. Okay, also an anti-tip over landing gear. We have what we're working on. We have 12 projects. I'm not going to go on to all of them because I don't want to cut our team short. This project is one of the biggest factors in all of aviation is crashing in a fire. And it isn't from rupturing the fuel tanks. It's from breaking the motor mounts. This is from our own studies. And pulling the gas line simply apart and the fuel leaking out through the gas line, making its way back to the gas tank, and then the fire erupts. So our team has worked out a fuel cutoff switch that is so advanced with redundancy features. I'm so proud of these guys. It actually has LiDAR, so it knows when to arm itself, so it's impossible to cut off when it's flying in the air. It's just not even a feature. But if you're really paranoid, it has a switch and you turn it off the circuit. Okay, but we can put 3 LiDAR sensors on it, and our team has developed a redundancy check so we can exclude one bad sensor, and we say it's a voting system, just like real aviation does for Boeing or anybody else. It has a software redundancy tech that we already have for other circuits, but this adds to it and gives us it becomes professional. What happens is you can set the G impact threshold level so that it will cut off before the metal deforms. Okay, if you have a hard clash, there are no more leaking fuel. It can't make its way back up before the impact, before the metal bends. And our team, UCSD, has just rocked it out of the park. In every area, they exceeded our expectations, except for the vendors. The COVID-19 has stopped some of our parts from getting here. I think it appears they were a little obscure. I mean, one they're going to send by September the 10th. I'm still trying to find that. So in every other area, though, I'm just so proud of all of these guys. We have far exceeded what we thought we'd be offering. And these are PRA's educational open source projects that we do try to sell for a little bit of money for all of this coding and the engineering that we'll be bringing out. But it's basically for education for the whole world and open for the world. And this is what pays for the parts, I hope. So it's a nominal fee. And it's a tax deductible donation also. So with that, I don't know if Chuck is here. Chuck really should be here. He is my right-hand man. I am technically the secretary, board of directors. I'm a secretary and officer, and I'm also the business manager. Essentially, I would be emptying the trash, but our airport is in Indiana, and I live in San Diego, California, not moving back there. Okay. So, but Chuck, without him, none of this stuff would happen. With that, I'm going to let our team, is Julius here? He's the one who has been the organizer. If not one, I'll turn it over to you to introduce not just yourself, but describe our team and a little bit more in depth of what our project is.
Thank you, John. So as John summed up pretty much, again, we're Team C. Our specific project is the enhancement of the fuel cutoff circuit that has been initially designed by an SDSU team. But our additions as a team was a user interface in which we could use to set parameter thresholds for any given gyrocopter, depending on the preferences of the pilot. In addition to that, we were also adding a switchboard circuit, which, again, as John said, it adds a redundancy and reliability factor in our LiDAR readings. To introduce ourselves, I'm Julius.
My name is Jorge.
My name is Juan.
I'm Warren.
And we're going to go ahead and start off with the motivation of this project. Sorry.
All right, so why are we working on this fuel cutoff circuit? Well, the main reason is safety. When your airplanes crash, there's a good chance that they'll caught on fire by the fuel that was in the tank. And the main reason why people die in these gyroplane accidents aren't really from the accidents themselves, but rather from the fire that comes after them. And the main goal of this project is to help save lives by preventing those fires. So as Julie said before, this project was designed by a different team. But the goal of our project is to enhance that previous system and make it better. We'll do this in 3 different ways. The first one will be to transfer the prototype that was given to us by our mentors, that can be seen in the left picture. And we'll move that to a PCB that can be seen in the other picture. The second thing will be to add a user interface, as Julius also said. It will have the user will be able to set parameters such as EGL, tip angle, and the G's. And we'll also be able to see certain parameters in a LCD screen. The final goal would be to add redundancy in the LiDAR readings by adding a switchboard that will create a more robust system. Here we have the flow diagram of our system. The pink stars show the main contributions to the project. On the top left, we have the set parameters, which is the user interface. So here, as I said before, the user will be able to input certain parameters that they want, and we'll also be able to see those parameters in a safety screen that will be going into a processor. The second will be the switchboard.
So we could keep settings and navigation throughout the app as minimal and easy as possible. In the case
that one of those will be malfunctioning, it would still be able to output a correct value into the processor. And then the processor takes in the user parameters and compares them with the sensor values. And if it gets a match, it will go ahead and cut off the fuel.
Right, so this is a processor we've decided to use to perform a majority of the tasks, as Juan explained. And the processor is the ATmega, which can be found on a standard Arduino Uno board. So by utilizing this chip alone and implementing it into a PCB with the required modules, which are listed below, the size of the original system that we were given can be decreased significantly. Another advantage to using this processor is that we can program it just like an Uno, which most of us have had some experience with in previous classes. In addition to this, by using the reference to the right, we were also able to streamline the process of transferring connections made in the old prototype to the new ATmega chip. So there are two sensors included in this project with easy to find source code either through web search or directly through the Arduino application. These include the TF Mini Plus for the distance above ground level or AGL measurement, and also the LSM9 DS1 for impact G-force and also angular orientation measurements. This is the LCD display that is used for both user interface before takeoff and also for continuous AGL reporting during flight. These are the last main modules, which include a 12-volt normally open solenoid valve, which is used for cutting off the fuel, and a dual transistor driver to supply power to the valve, given that the conditions are met. So this is the high-level algorithm used for the user interface code, which is contained within the setup function in the Arduino application. Inside of a loop set to repeat for the number of parameters to be set, which in our case is 3. Starting from the very left of this diagram, the software will wait for the user to choose one of either 3 inputs, either up, down, or continue. Depending on the input, the user either changes the parameter or stores it into an array for referencing later. After the third and final value is set, the program is then ready to run comparisons and then cut off the fuel if necessary. So here's a video showing the final parameter being set along with the transition into the AGL readings. And the reading here is going to be with reference to the ceiling. Okay, and here is a video of the valve switching in response to a match with the condition here set for the AGL. When you hear clicks, that is the valve closing and reopening in that order. Note that there is a short delay when reopening the valve for testing purposes, but also note that a long delay is required to allow for evacuation from the aircraft, given a real situation. That's the closing of the valve and a delayed reopening, and the same thing again. This is the circuit diagram for the processor PCB, including the required modules that were discussed before. And this is mainly to give you an idea of the excessive wiring involved without transferring to a PCB. And this is the PCB layout for that circuit, where all of the modules are to be mounted on top, including a 12-volt to 5-volt buck converter, given that our main source of power is going to be a 12-volt battery. And that module placement is here on the bottom left of the board. And just to point out a couple of other things, here on the top left is the solenoid driver placement. Here on the top right, we have the IMU board. And in addition to that, all of the other I/O that's required for this board.
Right, so now I'll go and talk about the main hardware design for this project, and that's been the switchboard circuit. And the objective here is to compare 3 LiDAR sensor readings and output 1 accurate signal to the 18 mega. And the purpose is to make the system more robust. Obviously, if you have 1 LiDAR sensor and that sensor malfunctions for whatever reason, you're now processing inaccurate data, and that could jeopardize the entire fuel cutoff system. In the case of a crash, it could cause the fuel line to not be cut off like it's supposed to, or even worse, it could cut the fuel line mid-flight, which is obviously one of the last things we want to happen. So by adding additional sensors in a switchboard circuit, we're able to ensure that if 1 LiDAR sensor malfunctions for whatever reason, the switchboard will be able to pick up on that and only use the 2 good LiDAR sensor readings to determine the output to the 18 mega. And that's kind of the principle of the switchboard circuit. It's going to compare the 3 LiDAR sensor readings to determine the output to the 18 mega. Here's a quick block diagram here. As you can see, you have your 3 LiDAR sensors on the top left. That goes to the switchboard, which has 2 subcircuits. The transistor logic circuit is where all the magic happens. That's where we're actually determining the output to the 18 mega. The comparator circuit provides 3 bits, which then controls a network and transmission gates in the transistor logic. But before we dive into that, we need to discuss an issue which we ran into, is that we actually needed a negative 7 volt supply to power op amps and also provide a negative reference value. So as Julius mentioned, if you go back, yeah, there you go. As Julius mentioned, we have one 12 volt battery, which is powering this entire system, the entire fuel cutoff system. So we needed to build a 12 volt to negative 7 volt voltage regulator. We decided to use an inverting switching converter for a number of reasons. This one in particular actually has built-in fault protection. So as you can see, there's a fault pin on the left-hand side of the switching converter. That pin will be internally pulled down to below 1 volt in case there's a fault. Obviously, that could happen from over voltage or over current. And if that fault happens, then the switching converter will turn off. It will actually reset, and that prevents it from damaging the component itself or anything around it. Obviously, we want to design the system in such a way where we won't hit a fault, or we won't even come close to hitting a fault unless obviously something drastic happens. Switching converters are also known to be highly efficient, especially compared to linear converters. By the time this regulator reaches steady state, it's drawing a little less than 0.2 watts from the 12 volt supply. We designed this circuit in such a way to have a startup time of 10 milliseconds and obviously an output voltage of negative 7 volts. So here we have a simulation. We have voltage on the y-axis and time on the x-axis. The red plot is going to be our output voltage. As you can see, that simply just gets pulled down to around negative 7 volts. It doesn't have to be exact for our application. It just has to be somewhere around there. Plus or minus 15% would even be acceptable. The main plot here is actually going to be the blue plot. That's going to be the fault voltage. As I mentioned earlier, that fault pin will be internally pulled down to below 1 volt. If there is a fault, we went ahead and marked the 1 volt line with that black line. But as you could tell, the fault voltage only gets to around 5.84 volts during the startup process. And that gives us good room for errors because obviously this is an ideal simulation. There's a lot of non-idealities that are not accounted for here. But we also decided to run yield analysis, which is on the next slide here. So this is a way for us to further test our design here. So what yield analysis is you're able to enter tolerances for a number of parameters, such as component parameters or even temperature. So what it does is it basically simulates a number of iterations. We decided to simulate 500 iterations. And what it did is every iteration for every component value, we entered in a tolerance, and it would pick a random value within that tolerance. So by running 500 iterations, we're essentially getting 500 different combinations of component values that might actually happen just due to the nature of component values. Obviously, resistors and capacitors have a specific tolerance to them. And as you can see, that didn't really change our output voltage like we expected. The only thing that really changed is the startup time, but that was just due to the tolerances of the startup capacitor. As you can see now, the fault voltage now gets pulled down to about 4 volts. So that's, obviously less than our ideal simulation. That's also expected, but we still have 3 volts. We still have a good amount of wiggle room to deal with other non-idealities, such as PCB fabrication. So back to the block diagram here. Now that we have that supply out of the way, we'll go and talk about the 2 subcircuits. So first, we're going to go ahead and focus on the comparator circuit. And what that's going to input, there's obviously going to be 3 inputs, the 3 LiDAR sensor readings, and it's going to output 3 bits. Each bit is going to correspond to the similarity between 2 LiDAR sensor readings. So bit 0 is comparing sensors 1 and 2, bit 1 compares sensors 2 and 3, and bit 2 compares sensors 1 and 3. And what it's basically checking is it's checking if the 2 readings are within an acceptable amount of error. And if it is, we're going to output high. Otherwise, we're going to output low. And the reason we're going to do this is because ideally, all 3 sensors, if they're all working correctly, they'd all be outputting the exact same value. If you're 10 meters above ground, they'd all be outputting 10 meters. But obviously, that might not be the case. One might be outputting 10 meters, another might be outputting 10.01 meters, and the third might be outputting 9.99 meters. So we're going to say, they're all within an acceptable amount of error. So obviously they're all working properly. And that's kind of why we need that acceptable amount of error to determine the bits. So this is kind of how we actually get our bits. So obviously we're comparing 2 LiDAR sensor readings at a time. We're going to pass those through a diff amp. That obviously just subtracts the inverting from the non-inverting input. That difference voltage is then going to be pushed through a window comparator, which checks if it's between a max or minimum reference value. This is kind of how we find our acceptable amount of error. You could set those reference values to certain voltages to basically correspond to be able to make the boundaries for the acceptable error. So if you go to the next slide, it kind of visualizes it a little more. So this is a simulation, voltage on the y-axis, time on the x-axis. What we essentially did is we just varied the 2 input signals. One had plotted the difference voltage, which is in red. That's obviously just the difference between the 2 signals. We have our max and minimum reference voltages in blue and purple. So obviously when the difference between the 2 signals is within that acceptable amount of error, our output in gray will get pushed to high. Otherwise it will get pushed to low. So that's kind of how we get our bits here. And those bits will obviously be passed to the transistor logic circuit, which, as I mentioned earlier, controls a network of transmission gate switches. So we're going to talk about that circuit next. So obviously here we need 6 inputs. We need the 3 bits and the 3 LiDAR sensor readings. And what we're going to do is output the average of the good LiDAR readings. And again, this is because ideally all 3 sensors will be outputting the exact same value, but obviously there will be some variation. So rather than determining which exact signal we want to pass through, we'll go and just average the 3 and pass them through, or average the good inputs and pass them through. And how we're going to average the signals, we're going to pass them through an inverted summer, then an inverter, and finally a voltage divider. Within those 3 stages there's going to be a network of transmission gate switches, which essentially controls which signals actually gets passed through. And in order to build those transmission gates, we decided to use a CMOS chip from Infineon. And this is really important because we were able to contact Infineon and get multiple levels of SPICE models. So we were actually able to run simulations using non-ideal parameters such as on resistance and parasitic capacitance and even temperature variation. So another reason we use these chips is it had low on resistance for the cost. And obviously that's just to minimize the amount of loss we have in this circuit. So here's a quick block diagram of the transistor logic circuit itself. As you can see, the 3 LiDAR sensors are the main inputs that goes through a network of transmission gate switches, which determine which signals actually get passed through to the inverted summer, then the inverter, and finally the voltage divider at the end, which then determines the output to the 18 mega. And here's a schematic here. It's kind of hard to follow, so we went and unboxed each stage here. Starting from the top left, you have your 3 branches. Those are your 3 inputs with the transmission gate switches. That goes through an inverted summer, an inverter, and a voltage divider with more transmission gates at the end. Obviously, it's hard to determine what exactly is going on here, so we went ahead and broke it down to the 3 stages. Stage A is just obviously the inverted summer. It's just summing up the 3 inputs, then multiplying by -1, basically. That inverter is there just to bring that voltage back to positive. And finally, the voltage divider at the end is to determine the exact denominator we want at the end. Because obviously, if there's 2 inputs, we want to just average 2 signals. If there's 3 inputs, we want to average all 3. And of course, we wanted to run as many simulations as possible. As I mentioned, we were able to run non-ideal simulations thanks to Infineon. So this simulation here was actually ran with the on resistance of the transistors themselves. So the purpose here was to determine how much loss we actually have through the transistor, through the transmission gates. So as you can see, we have a truth table on our bottom right that just kind of cycles through our 8 cases with our 3 bits, as well as our expected output voltage on the right-hand side. We have our test values on the top right. Obviously, those aren't very close together, and that's simply to help us visualize it on the graph. Obviously, if they're all within, if they're all 3 are really close together, then you basically just have a straight line across. This way, we could actually see some variation. And the plot itself, it kind of just cycles through all 8 cases. We kind of labeled them 0 through 7 there. And what we wanted to do is check the simulated value, which will actually give us an approximated loss through our transmission gates with our, obviously, our ideal value in the truth table. The maximum deviation actually happens in case number 2. As you can see, our output, our simulated output is 4.481 volts, and our ideal output would be 4.5 volts if there was no loss. And that's just a maximum deviation of 19 millivolts, which is much better than we expected. So this is just a kind of a way we're able to confirm that there won't be too much loss in the circuit that might jeopardize the system itself. And now we'll go and just talk about the PCB design for this project.
So here we have the complete Altium designs for both parts of the switchboard, the comparator and the transistor logic. So due to delay of parts, these boards were not able to be tested, but the next year we'll be able to test within PCB designs in hand.
Here we have the complete design for the converter, which will be fitting the comparator with -7 volts. This design was the first one to be finalized since it did not have to wait for the LiDAR sensor to be tested in case of any different values that we needed for the switchboard or the comparator. So even if we did need new components, these components will retain its same sizes, even if have different values. So the other 2 boards were built in Altium since they also had to be changed. So we took the time to learn Altium and give them an industrial finish. Here we have the physical boards with some of the components soldered into them. Most of these components were received early on, but the main one that was needed for testing was the actual switching regulator chip that can be seen in the center. So we have a total of these 3 boards, so the future team can test them once these switching converters arrive. And also once the whole PCBs are tested, it could be combined into a single one. So for our project impact, its mainly impact is on safety and gyroplane flight, since most of these gyroplanes don't have these enhancements built in. Most of these enthusiasts can buy this kit and put it into their own gyroplanes. The economic impact is we stayed way under our budget of $500, so it will be very affordable to these enthusiasts who want to have these enhancements on their gyroplanes. And since PRA has a great reach over the United States and also around the world, this kit can be easily globalized and be accessible for all their members. So now Julius will cover our milestones.
So here are the milestones that we set in the beginning of the quarter, highlighting what we were able to achieve with the given time we had. Again, we were able to design and test the user interface along with the valve switching response to the set thresholds. We also finished the design and simulations of the switchboard and its subsystems. Unfortunately, as we mentioned, we weren't able to assemble and test the PCBs we designed due to various issues with shipping. Of course, this kept us from testing the entire system as a whole and getting housing design for the final product. Again, the main challenge was getting our parts delivered, but we are happy to say that we got the main design portions of the project completed with the continued support of our mentors. So if there are any other questions that you guys have, feel free to ask them now.
Thank you, Team C.
I have a few.
Go ahead, Jack.
Okay, so just hope you guys realize that how important it is, because you have lives involved and you have probably loss of material involved if there is a failure, right? So I don't think this is ready to fly, and you should talk to a sponsor to really test this beforehand. And I'm going to give a couple hints, right? When you power on inductor, what's the problem when you remove the power for an inductor? Like you have an inductor, like a relay or anything like that, a solenoid. When you're on and off, I'll help you, right? So as soon as you remove the power, so that thing has to discharge somewhere. I have to make sure your circuit that drives the solenoid is ready to discharge that with a diode. There are circuits out there, so that other than that, that whole peak power come back to your circuit and it become a noise. And that's a clue for microcontroller, right? Make sure that your circuit that power on and off the solenoid is meant to power solenoids, right? So the next part that I have for you to take a look is, do you have any non-volatile memory on a microcontroller? Or every time someone turn on and off the circuit, they have to program again?
No, there's volatile memory. There's non-volatile memory on there. And I'm John Roundtree, the sponsor. I have a question for you, Jack.
Yeah.
You said it needs to come off the solenoid, a master solenoid.
The driver for a solenoid, right? Every time you turn on and off a solenoid, you have to have a little circuit that protect it. If your circuit that the students already selected was meant to drive solenoid, should be in there. I just asked them to check.
Okay. Right? There's a 12-volt separate battery, rechargeable.
That's not it. That's
okay.
Not
I wanted to make sure I understood.
Ask them to go do some reading about how to power solenoids and then how to protect the electronics that power the solenoids. Right? It's pretty normal.
I believe that's the point of the diodes in the switching converter schematic. So we ensured that it was rated high enough for that.
Well,
for current and voltage, or are there more aspects that we should be looking into?
It's a discharge aspect of it, right? So you have that all magnetic field. As soon as you remove the power from it, instantaneously it has to go there. It's no longer 12 volts. It probably could be bigger, right? Just to make sure it gets driven somewhere to ground, for example. You may have the solution. I'm just raising it that we're not going to have time to discuss this.
Sure, I understand.
Just make sure you go to the next one that come about you, right? The other thing is that there is no reason why I didn't use a microcontroller that has non-volatile memory, because I'm assuming I have the same setup. My settings probably going to be the same for every single flight, unless I change my design or something like that, right? So go take a look on a microcontroller that after you write this, you can put in a non-volatile memory. It's very few parameters. I have even some Arduino-based microcontroller have that, and I'll get to the point why I should be using Arduino next, okay?
You're right about the parameters except for one, the total gallons. For instance, we're also doing fuel flow totalizing hours.
Right. So what I meant is that if I don't want to change the parameter, and I don't, but I rather use and don't go every time, click, 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 click.
Right, it has that it has so much non-volatile memory on that chip, on that NILS chip.
It does or it doesn't?
It does. It has both. That's one of the reasons we selected it. It has both. We can burn it and we can keep it there.
So that's what I was asking, if that chip has no volatile memory, and then I'm not sure if I heard that. Okay, so the other part why I think you should not be using this microcontroller. Have you heard about Watchdog or not? Do you know what it is? If not, I can explain to you. What is a Watchdog on a microcontroller or on a computer? Do you have an idea what it is?
I have an idea of what it is, but we've had watchdogs that watch circuitry and software for certain.
And I was not necessarily directing the question for this. I'm trying to make this student. All right, so you have 3 different inputs coming through. What if your software locks? Who's taking care of the software? Go read about Watchdogs and that's why you should not be using that microcontroller. All right, you should be using something with watchdog. The other thing is that what if the fuel valve fails? Do you have an overpass that the user mid-flight can overpass? I mean, you understand? You have all this redundant, and you have one component that can fail. And that can bring down, that can lock up, that can lock down. So think about that, right? Either is really, really good, right? It was meant to be that. And that's coming from my next question, that you're pretty sure that they're not going to fail because they have a high reliability information, and you can get that out of a sheet, and people guarantee that that stuff will survive, right? But I would think about it, okay, it's all beautiful redundant the electronics, and then come to the mechanical aspect, yep, that valve may break. And then
the other part of that is you could put real easily GPS tracking that matches the distance, and you're using the GPS.
Well, what I meant is the mechanical valve, right? What if the mechanical valve fail and then I shut down the fuel mid-flight? Got it? So just think.
Oh, sure.
Okay.
But, you know, we've been having failures in aircraft since they first were invented.
Right. And then this
1,000 hours, I put 3 planes down because valves failed.
Yes, right now we're just raising something that the next group can go work on. We guys have no time, right? So
these are good ideas.
And the other,
obviously, there are a lot more safety parameters that could be implemented into the system.
Yeah, just like getting the people that come next, right? This is called reliability engine. Turn out my PhD was in this. That's why I'm picking on you, right? So that's why I studied in graduate school. And then the other part is that this whole electronics has to be tested for environment testing, right? So there are, and then John probably can get to this. Like the people put this on a shaker, put that on some heat, right?
It's actually created by mechanical engineering students at San Diego State College, and that's why it's in Arduino format. They were not EE students, so I could not get it there. Okay, and that is the process that has been done. The angles, the tipping, the warping, smashing it until it's like 12G, and everything else is broken. What happened to the circuit?
And then you have like service provider, just send the board. And again, you guys don't have time, right? Just your recommendation, because now you have a name of something that impacts lives. Do you realize that, right?
Absolutely.
You sign your name, right? So make sure that all you're doing now is making all the recommendation and taking care of liability, right? By saying this is no way ready to fly.
It's a educational open source project for experimental aircraft. Just as we build our rides are all experimental, not one of them.
But I would like the UCCD students to put in there that's not ready to fly. All right, that's further test has to be done.
Oh, absolutely. We're not selling this even now until we're just now got it to a commercial point where we can test the final project.
Okay, and the next part is, did you take a look on analog signal noise? Because it seems that your LiDAR is analog, not digital, right? So analog signal get interference for a bunch of stuff. What if I have some interference there, and then they come from the wires, because those wires work as antennas, right? And now you think you have that signal, but you don't have that right signal, right? So that's
Yes, we tried to minimize as much noise as possible, especially from the switching converter, because that obviously itself could. And also with Juan and Jorge, they looked at a lot of EMI. A way to minimize EMI and PCB design as well. So that is something that we took into consideration.
But I understand, right? You couldn't have put this on the aircraft, and you couldn't test it. So the people that come after you,
we shield the cables.
Has to do this.
We shield the cables anyway, grounded, shielded cables, just like our spark plug wires and everything else.
Right. So exactly the point, right, John? I'm just raising this, and then it'll be a check. People say, "Hey, yeah."
I love it. I thought of most of them. The Watchdog chip, you have one that you would suggest using?
Well, there are so many. Like you look for the XTM32. It's pretty cheap, but it has a Watchdog, and then just for the education for students. So Watchdog means my software is running, and I have to go to the member and say, I'm alive, I'm alive, I'm alive, every 5 milliseconds, 10 milliseconds, 100 milliseconds, doesn't matter, right? You set that. And then if you don't go to that says I'm alive, you're going to reset the microcontroller and it come back for a lockup space. Got it? That's why I wouldn't let my family fly on Arduino microprocessor. Got it? Just for this kind
we actually have systems that are designed to talk to other systems, like the fuel flow totalizer, and share information. That does have a watchdog system for all of them. It's a master.
Exactly, John. So that's why I wouldn't. It's like I get it. What you guys did. I got a training on that. I learned at school, right? And then it was easy for me to integrate. But you have to think this whole logic. What could go wrong with this? And did we think about everything that could be wrong? And if it does, can I detect? Right? That's failure mode and effect analysis. If it happened, can I detect? What's the consequences? Then you make a list. And then now what can you do to reduce that number, right? You do have to ask the people that come after you to go take a serious look on this of everything that can go wrong, and within reasonable and with some cost, improve it.
Sure. The good news is you can just turn a switch and it's totally cut out of the circuit to open switch fuel system. Like it's not there at all. It really only comes to an effect when you're you set it for about a foot off the ground. So the only impact is it could turn off in the air when you're flying or taking off, and that's where we really got to concentrate because of where we're shutting this thing down is so close to the ground. We don't spend much time there. Okay, so the danger time and time spent outweighs a lot of our concerns that I've had that you're expressing now too.
Yeah, no, I mean, good point, right? That's why I asked, hey, is that a bypass to the valve? And then I couldn't.
Yeah. So, but the point is that they're well taken, and this is what PRA is all about, is looking at all these.
And then as long as this team take a note on this stuff and pass to the next thing that's coming, so they don't have to rethink this. We already give some thinking on that, right? And more important, that disclosure, not ready to fly, please. Yeah.
No, it's not ready to fly, or it's not even offered to put up anywhere on the website. We've got to have a finished model, and then we're going to go out and crash it in a real pyro.
So I hope you guys are open for my feedback and know where I'm coming from. That's why in school to learn, right? To get people that maybe have a little bit more years experience than you and tell you it's not a criticism. It's just trying to add the people that come after you can do some other stuff. You have a chance to just go over the guys from Team
I never understood criticism or took it personally. I only saw a way to think of a solution when it's off ever, my whole life. I mean, I just don't get this. There are no criticisms, only I got a problem we got to solve. Okay, I'm good at that.
All possible problem, John. That's what I was trying to get to the students to think this over, and then pass the ball to the people that come after. You don't have time. That's it, right? That's your final presentation, but you can capture those things.
Yeah, thank you very much.
You're welcome. Cool project, John.
Thank you, Jack, for all the questions and comments. Okay.
I just want to thank you all for thinking this through, because when you're up there hanging your life on it, there's no time for mistakes. So thank you so much for your input.
Thanks, Chuck and John, for mentoring all the students. Okay, great. Now we will move on to Team D.
All right, so that's me, isn't it?
Yes.
Mentor is Jack.
All right, hey guys. Oh, looking good. Hey, listen. So this is probably my 4th years with 191 students, and I usually try to bring them to work on a project that's close to home at UCSD. I manage a couple projects at UCSD, and then that's one of the robots that you see over there. And one of the problems we have, and it's for every single robot that you're probably going to see in your life, is this power distribution, right? So there is a battery come here, and how do you get power to go to other place? That's one that would go on that robot. See how ugly in the sense of that we have to manage all this. And then imagine I'll put this on a robot submarine. It has maybe double the numbers of the actuators, and then have probably 3 times or 6 times more wires than this. And some of those are relatively thick wires, maybe 10 gauge. So that's the problem that I asked this team to go solve for us. Go ahead, fellows.
Hello, I'm Mohammed Odemad, and this is Team D for the Smart Wheelchair. My partners are Johan Terral Salcedo, Daniel Renfro, and Khalid Al-Rabi. So the purpose of this project is to design 2 PCBs using the Eagle software. The PCBs are power distribution boards that are meant to deliver a fixed amount of electrical voltage and amperage power to the device's components from the main power source. The two PDBs are PCB4, which will first go into an autonomous vehicle, and PCB5, which will be used in a RoboSub competition. And once the boards prove to be effective in these devices, they will finally be deemed acceptable to be used in a low-cost smart wheelchair. Next slide, please. Now, we thought that this project would be useful to invest time and resources on due to the steady growing market for electrical wheelchairs. It is estimated to exceed $2.9 billion by 2026. Not only that, but by 2030, there is expected to be a 75% increase in wheelchair use by the 65 and over age group. And even today, there are roughly 65 million users worldwide. Aside from the lucrative aspect, electrical wheelchairs are also a more efficient replacement as they allow for more independence compared to manual ones. And there are currently around 20 million individuals who can't get access to any wheelchairs. Next slide, please. Now, the goal specific to our team involved having two functioning PDBs in hand. And these PDBs had to be adjusted so that they take up the least amount of space as possible, while also not making the board overly complex with where its inputs and outputs are located. So in short, they have to be small, compact, and user-friendly. As a reference, the circuit below is what we're dealing with before older models, and the circuit above is more what we're trying to achieve. Next slide, please.
Hi, I'm Daniel Renfro, and I'm going to talk about the methods of search for the 3 power converters that went onto each board. So at the beginning of the quarter, when we nor Dr. Silverman really knew the best way to search for these converters, we were endlessly searching through chip schematics, just hoping to get lucky and find a schematic example which gave us the exact input and output requirements which we needed. We actually were successful for 2 different converters using this method, but the 5-volt 10-amp converter being high current proved difficult. Eventually, we found a resource called TI Webbench, which allowed for simulation of different TI chips to get the exact input and output desired. This source showed data such as efficiency and cost, and after reading online reviews, we decided this was a reliable source. Next slide. Now I'm just going to give a brief overview of the converters used. In the block diagram shown on this slide, you can see the general functionality of PCB4 version 1 and PCB4 version 2. The converters which go on each of these versions will be discussed further on later slides. These versions are fairly similar other than the size of the boards and one of the converters is switched out. As you can see in the diagram, PCB4 originally had a 3.3 volt 3-amp converter, a 12-volt 5-amp converter, and a 5-volt 10-amp converter. Due to the large size of the 5-volt 10-amp converter, this was changed in the later versions to a 5-volt 5-amp converter. Right, next slide. PCB5 has a 9-volt 5-amp converter, a 12-volt 5-amp converter, and a 5-volt 10-amp converter. Although next quarter, I imagine the 5-volt 10-amp converter on this board will be changed as well, due to the size resulting from the current. These converters are going to be used to power an electric speed converter, single board computers, cameras, LiDAR, as well as various other robotic sensors. Okay, next slide. This 3.3 volt 3-amp converter was one of the converters we found searching through the schematics. It was not available for testing in TI Webbench, but the data sheet was absolutely full of various tests, such as efficiency in varying conditions. We used this exact model to build our model in Eagle. The graph on this slide shows how the efficiency, which is on the y-axis, is related to the output current, which is on the x-axis. As you can see, this circuit is very efficient when there is an output of 3 amps. Okay, next slide. Here are the simulation results for the 5-volt 5-amp converter. And as you can see, based on the axes, the variation in voltage and current is quite small. This is the converter which is replacing the 10-volt 5-amp converter due to size constraints. And the number of components for the system is small too, which saves a lot of time in terms of finding equivalent parts and placing them onto the board. The red line on the graph represents the ripple in the output voltage, and the ripple is quite small. The gray line and axis on the right represent the output current, and it is a very smooth line. This small ripple in the output helps with the efficiency of the system. right, next slide.
Alrighty, I'm gonna talk a little bit more about our converters. And this is our 5-volt 10-amp converter, and it's our high current output and converter. It has the highest current output of all the converters on both boards. And the board layout for this converter necessitated a careful polygon design. And polygons act just like traces, but they have large surface areas, and that's used to accommodate high levels of amperage, effectively creating a wide path for current across that wide surface area. And to calculate those necessary surface areas, we utilized online trace calculators, and we use that to estimate all traces, all connection traces of polygons. Anywhere current is flowing on the board, we use that calculator to make sure functioning. And because of the high current levels, this particular chip, this LM3150 chip, has an exposed die attached pad on the bottom that's connected directly to signal ground and the board's ground plane to help dissipate the heat out of the IC, out of the chip. And if you look at the graph on the right, it shows the simulation for the converter, and efficiency for this converter was actually pretty high at 93.4% with a voltage ripple of 34.43 millivolts with a 4.99 average voltage output. Excuse me. Yes, so next slide, please. All right, unique to PCB5 here is our 9-volt 5-amp converter. And this design was not difficult at all. There were many chips available on this board. Are we looking at, okay, 12-volt 5 amps, I'm sorry. So this is our 12-volt 5-amp converter, and this one was pretty interesting because of its input. Now, the input for our design specifications, we needed it's a variable of 12 volts input to output of 24 volts. And if you look at this guy has a 12-volt output. So at minimum 12-volt output with 12-volt input with a 12-volt output, that's a 1-to-1 ratio. And that's effectively a 0-volt step down, and the chip is a step down buck chip, right? So it was difficult to design on our own. So we were really happy to have TI's web bench. And the final design for this one is a little different. It's actually, it needs a 12.4 volt input to 24 volt input range. And the actual output, it's actually 12.12 volts. So the energy difference there to do that step down. And the graph on the right, if you take a look at the axes, you can see the V out showing that 12.12 output in red on the left there, and on the right in blue, you can see the output, the current output at 5 amps output in the blue, which was constant. Had a 90.3% efficiency rate and a 0.3 volt ripple. Next slide. And again, this is our 9-volt 5-amp converter, and this was one of the easier ones to implement, and it wasn't too difficult. There were many chips that could handle this guy, and we went with the LMR 140050 chip because it utilized the least number of associated components, thus decreasing our bill of material costs. And so the graph on the right, if you take a look at this output voltage in red, it has an interesting voltage waveform. We didn't dig too much into why it looks like that. We're sure it's something to do with the capacitances, etc. But in red, you can see it came out at exactly 9 volts average, and with a 91.1% efficiency and current exactly at 5 amps output. Next slide, please. All right, I'm going to talk a little bit about our component considerations and the details that went into that, which is more than we initially thought. We thought this would be the easiest part of the project, but it turned out to be pretty involved. And we had to consider different factors, and some of the design constraints. We had to consider whether we're going to use the SMD or through-hole for soldering our cells for reasons teammate Khalid will explain later on in the presentation. Another design constraint was the component packaging, which was a bit of a headache, but we got around it. Sometimes packaging came in cut tape, that's the one we wanted, where you could purchase one item at a time, one component at a time, but oftentimes many components came in bulk. You have to purchase 1,000, 2,000, 5,000 at a time. So that limited our options for equivalent components. And also the passives, much more to consider than Farad and Henry values. We had to look at for capacitors, for instance, the ESR, its temperature coefficient, its tolerance, etc. And for inductors, along with its inductance, its DC resistance, the core material, what it's made of, whether it's shielded or unshielded, and its current rating as applied to which converter we're using it in. And next slide, please.
Now, huge difficulties that came with using Eagle was its sizable learning curve, made all the more difficult with its scarce online resources. Eagle is a fairly obscurely documented design tool online with limited information. As such, it was fairly difficult to find out how some tools functions and their limitations. The tutorials that were available, though, also omitted crucial information on the design tools, which led to many redesigns. One of the biggest cases of these redesigns involved a time when we used the regular tracing tool on the software's board to wire our components together in our PCB4 design. We would have saved 1 to 2 weeks of time if the tutorials had mentioned that the regular traces can afford for the electrical power demands of boards such as ours. It instead brushed these crucial details aside, and thus we had to redesign our boards. We spent days looking for an alternative, and we found it in the form of polygons, which also took many websites to research on, as there are a few handful of Eagle tutorials that explains how to use the polygons for purposes other than making a ground plane. We had to deeply research and commit to trial and errors until we could be certain that the polygons act as copper connections to the board's devices. An almost equal amount of time was also spent learning how to design custom footprints and parts in Eagle, as there weren't pre-existing libraries for many parts that we used in our design, and getting the functionality and dimensions of the custom parts right took multiple tries that had us go back and fix the board on a few occasions. Next slide, please.
So right now, I would like
Canvas
to
and
highlight
Piazza.
some
the
difficulties
revenue-
and challenges we faced with JLC PCB. JLC PCB was the manufacturer that we decided to use. When we first designed our first board, PCB4 version 1, when we were checking out on the website, we had everything ready. As we were checking out, we learned that JLC PCB has a limit on extended parts or components. JLC PCB as a manufacturer has over 33,000 components, 600 of which are basic and the rest are extended. Basic components are resistors, capacitors, inductors, and chips that are most commonly used. Extended components are also these same components, but with different or less frequently used specifications. As an example, in one of our converters, we're using an 8.2 microhenry inductor that had to withstand 5 amps of current. While we did find another basic 8.2 microhenry inductor, it only handled about 500 milliamps of current, which was nowhere near what we needed it to be. Another challenge we faced was out-of-stock parts. Out-of-stock parts were only shown at the end of the ordering process and led us to redesign our boards and remove SMD components and replace them with through-hole components. On the right, you can see a picture of the checkout page where, because some components were out of stock, or because we exceeded the extended part limit, we were not able to confirm some components on the board. We did some other manufacturer research to see any other options that we may have and may be able to use. But the problem was that other manufacturers did not have a library of their SMD or SMT components. So we were not sure what parts they have and what parts we can use. Another problem we faced was that many of them had very long lead times, up to 25 days, which, as opposed to JLC PCB, which has a lead time of about a week, was very long. So for the impacts of our project, as a higher picture or higher view impact, ultimately the boards will be used in a smart wheelchair. So currently the cost of a power wheelchair, not even a smart wheelchair, averages at $7,000 going up to $30,000. So what we hope is that this project will ultimately make a cost-friendly product that is available to a wider range of people and people of different income. For our accomplishments on this project, we successfully designed Eagle designs for both PCB4 and PCB5 by creating the necessary footprints and symbols we need to use on Eagle. We did many redesigns based on the size of the boards, as we needed to be as small as possible to fit on the autonomous vehicles and the RoboSub, which is going to be used. We completed manufacturing of PCB4 version 1.0, which is shown on the top right. But unfortunately, due to a design error with the connectors, we were not able to test it. But that was a learning opportunity for us and allowed us to fix the connectors on PCB4 version 2 and PCB5. We also successfully ordered PCB5, which is shown in the bottom right. It is expected to arrive these few days soon, and we will test it after it arrives just to make sure that everything works as expected. For future work, since this project has been with ECE 191 for quite a few quarters, for the next quarter students, our recommendation to them is that they should find a way to eliminate through-hole component use and use SMD components instead. This will help make the boards even smaller. As you can see on the right, this is a picture of PCB4 version 2. As you can see, we have a few through-hole components such as inductors and capacitors, which take up a lot of space that can be saved. We will also complete the ordering of PCB4 version 2 so that it is ready for testing for the next students who take over. In summary, throughout this quarter and with this project, we've accomplished many things. We researched resources, found WebBench, and that allowed us to be more efficient in our work. We learned Eagle functionalities and used those to help us move forward with our project, such as in making custom parts that were not available and using the polygons. We found the converter circuits and researched their exact components, either on JLC PCB to be surface-mounted SMDs, or through DigiKey, where we ordered our through-hole components. We designed 2 versions of PCB4 and PCB5, and we ordered the boards and their equivalent through-hole components. We're open to questions if you have any.
Thank you, Team D. Any questions from the audience?
I have one. If you would start again, what would you do different?
Sorry?
If you were starting again, right? Go back 10 weeks.
Yeah.
What would you do different?
Okay, I got something to say. So in the beginning, I mentioned searching through schematics for converters, and I think and thought like there's got to be a better way to do this. Then that would have saved probably 3 or 4 weeks of time. But I mean, we didn't know any better.
Yes.
But now for the future, I think we kind of learned our lesson in that regard.
However, that search to design without the assistance of WebBench made that search and the stuff learned in that search made feature, even though it was maybe a wasted 4 weeks, it made, after we found WebBench, everything became much simpler in terms of like the chip part search and such like that. So it's like digging around, trying to design and reading through data sheets familiarizes you with the details in the converters themselves. So it's like, it was like a two-sided sword, or what's the word for a double-edged sword or whatnot. But I mean, but I would pass that information on to anybody who's doing power distribution boards going forward. TI's WebBench is like heaven, you know.
Good. One other question about your simulation results. I saw that you plotted the voltage. The voltage does match expectation on average, but there is some fluctuations. Does this matter?
The fluctuations meaning ripple?
Yes.
Yes, ripple output voltage, it does matter. If you look at the 12 volt, I believe our 12 volt has actually the highest voltage ripple with a 0.3 volts. I mean, it does matter for you know, I mean, yeah, the average
Well,
voltage.
so if you want, your user can answer that to you. So the answer would be no, because the input voltage for the circuits that they're going to be doing, they have like between 3 voltage variation that's tolerant. So that 0.1 and 0.15 volts will not matter because the circuit itself has another.
Okay. But we wouldn't want something like a 1 volt voltage ripple.
Yeah. So in this case, it's not.
Right.
And for example, one of the single board computers that are going to be powering out of the 12 volts, it can be power from 9 volts all the way to 18 volts.
Got it.
Yeah. And the reason we put 12 is because it's pretty common to power other things. So we just, okay, let's get 12. And then since this computer going to work with this, the next computer coming also and no work with 12 instead of making simply that to be 18. Yeah. So for their application, it doesn't. And that's why we thought it was okay. Remember when we were doing dry run yesterday, they have some graph that showed the ripple being, this size. And so, guys, this is not a very good message, right? Even though I can see the scale, you're going to ask all the users to go take a look at that and say, less than 0.5 volts. So, 0.2 volts. So I have to read that, just show in scale what it looks like. If you take a look, if you just put 0 to 10, this look like really small. Yeah. Okay. All right. Good question.
Got it. Any other questions from the audience? Okay, good. Thank you, Team D, for your presentation. Now we will go with Team E, our last team. And the mentor are Manao and Jinpei from EVT. Are you here?
Yes.
Hi, Manao. Thank you for coming. Do you want to briefly introduce yourself and your team?
Sure. So my name is Munal Parmar. I'm CEO of Educational Vision Technologies. We have a system which uses artificial intelligence to autonomously generate online courses. So we can rapidly convert all of the university's physical classes online and do it in such a way that the online courses are very efficient and engaging. We have customers with a few departments at UCSD, and just from the feedback for this quarter was that the students in the math department preferred EVT's online courses versus all of the other lecture delivery methods that their students were using. So yeah, and we're with COVID, all the universities are moving online, and they're using quick implementations, and we provide a quick way to go online, but with much higher quality. So yeah, our team is recruiting. So if you are looking for summer internships or fall internships, or for a full-time job, we're very interested in talking with you. Just feel free to send me your resume, and we can have a conversation.
Great, thank you. If you, any of the students, if you want to contact Manal and you don't know his contact information, let me know. Okay, Team E, please start.
Hi everyone, this is Team E, and our project topic is about speech recognition. I'm Gao Tongwu here.
I'm Abhijay. I'm Elliot. I'm Chao Ping.
Yeah, and the project is sponsored by EVT, and Mona and Jinpei are our mentors. As the mentors say, like EVT, here is some background information and motivation. EVT is a company using artificial intelligence to generate lectures and study material for the students, and they can provide automated audio and visual transcript for the lectures. So as you can see on the right here, this platform is generating transcript of what the lecturer is speaking, and it prints out the transcript on the screen. However, the company is currently outsourcing speech recognition to paid service. So because of the improvement in some existing open source speech recognition models, they're actively preserving them as a viable alternatives to the paid service. So that's why we're doing this project. Here are our initial goals we set up at the beginning of the quarter. First of all, we are going to create a benchmarking tool to analyze the accuracy performance of those models. And then we are going to implement those pre-trained models for transcription and compare their accuracy performance. Those models include Mozilla Deep Speech. That's what we start with at the beginning. And then we move on to CMU Synfix, Google speech-to-text models. After that, we're going to deploy the framework onto the server for remote functionality. At the end, we're going to improve model accuracy through domain-specific vocabulary. Here we want to introduce the concept of RNN, which refers to recurrent neural network. Because our project belongs to the area of natural language processing, so we need to use RNN to train all the models. RNN is a sequential memory network, which means the output of the previous cycle goes into one of the input of the next cycles. This is like when you are predicting the next word, we not only need the information of that word, but also we need to know the context of the sentence, of the paragraph, or even the whole article. And that's why we need to know the information about the word which already generated before. And the input data is broken into pieces, just like the input sentence is broken into different words, and each word is sampled as a vector and goes into the input. At the end, the RNN is connected to a feed-forward network, and then it's for a classification purpose. This is how the models we are using are trained.
So we want to use different softwares to translate what the speaker is saying, but we need a way to know how well each software is performing. So this is where word error rate comes in. Word error rate is the main measure of accuracy that we're using to assess the level of performance. So after we run the software, we get a text translation of the audio, and we compare the output of the program to a text of what the speaker is actually saying. We look for substitutions, deletions, and insertions of words. So word error rate is the sum of all the substitutions, deletions, and insertions divided by the total number of words the speaker is actually saying. So in our project, we are using Ben Lambert's open source implementation of word error rate. So for the accuracy framework itself, it takes an audio file and a reference text of what is actually being said to compute the word error rate. The length of the audio can also be specified, and it will trim the audio and run on only the specified amount of time. The specific models for each software can also be given, and it will run on only those models. So these are optional, and by default, it will run on the full audio file and on the default models for all the softwares. So all the audio conversion to different formats and frequencies is handled in the framework, and the user can just provide an MP3 file and get the output. So it will take these inputs and display the word error rate of each model, the best word error rate and its transcript, and the estimated best transcript that the framework thinks has the lowest error rate without using any reference. It will also store the final audio file, the word error rate of each model for later analysis, and a transcript generated by each model. So if you want to look up what the output for a specific model was, you can ask for it, even if it doesn't display by default. So an early problem that we identified was that for some audio files, it was difficult to get a reference text. And it was tedious to write reference text when we just want an output. So if no reference text is provided, then this is how we estimate the best output to display to the user. So it looks for same words. So if two software both have the same words, then the output, then we can be pretty sure that it's right. So then it looks at the average word error rate of the data that's stored on the server. Like we mentioned, every time you run, it stores the word error rate. So it uses the average of the word error rate as a weight to decide which output is the best. So confidence index is also used as a weight. So each program gives the confidence level for each word, and we use that as a weight. And basically we're using these three factors to make a decision on which output to display. So same words and average word error rate are given more priority than the confidence than the confidence index. This is because the confidence index is unique for each software. For example, if DeepSpeech is 70% sure of a word, and Google Speech is also 70% sure that it gets the word right, it doesn't necessarily mean the same thing. So this is the basic way to display the best output to the user without having a reference text file. And when we ran it, we found that it works fine for short clips, but unfortunately for longer audio clips, it's not very easy to decide which output is the best without a reference file. This is because the number of substitutions, deletions, and insertions increase, and computing the weights itself becomes a problem. To summarize what we're displaying by default, we are displaying the word error rate, like we mentioned before. We're displaying the word recognition rate, which is basically the opposite of the error rate. We're basically displaying how many words we got right. And we're displaying the sentence error rate. So this is basically the word error rate, except on a sentence level. So this is useful for programs that have built-in grammar support. And we're displaying the lowest word error rate and the transcript for the lowest word error rate. And we're just displaying the best transcript that we can get without using the reference file. So this is how the output display looks. So the accuracy report can be displayed in the command line, and you can also get a text file with all the information. So if you want to download the text file, you can. And as you can see, it's displaying the word error rate for the three softwares. It's giving you the best word error rate, the transcript, and the best transcript that it can get without using the reference file. So we ran a couple of audio files through the framework, and we plotted the word error rate of 10 long audio files and 10 short audio files. So the long audio files are basically lecture videos of ECE lectures, about 50 minutes to more than an hour long. The short audio files are clips from an online dataset that we downloaded, and some we recorded ourselves. So the three plots at the top are for our long audio files, and the three at the bottom are for short audio. As you can see, that the word error rate is much higher for long audio as compared to short audio. This is probably because of factors like noise, pace of speech, and the number of speakers. In lecture audio, there might be a student asking questions, and the pace of the lecture might be dramatically different from how you would speak when you're issuing an audio command or having a conversation. So software like DeepSpeech and Sphinx aren't really optimized for this, and so that's probably why there's the performance is very bad on long audio files. Scientific vocabulary, especially, is a major source of errors for these lecture videos.
So there's going to be many requests for transcription simultaneously, which requires there to be a scalable implementation of the previously mentioned framework. And so the implementation for this is a package called Luigi, which is a task scheduler that allocates server resources efficiently and gives a visual representation of things that are running currently and things that have been completed. This facilitates running many different models at once and automatically processing the input from the lectures into a usable format. This can be used by people connecting remotely to the server in order to run Luigi from a central interface instead of having to run it from on the server. It also gives a single one-line command that can be used to run many different models at once with potentially different lectures and have them output to a JSON file that will categorize the lectures along with the models that they ran on. So there's a flowchart here that shows the process that Luigi follows. It starts with the user requesting a new command, which would be a lecture and some models to be processed. and then it issues first a task to process the lecture to be read by each of the models, and then it assigns the processed lecture in task 2 to each processed lecture to its corresponding model in a Hadoop job, which will allocate as many resources as need be to run the task. And then task 3 takes all of the outputs of the models and puts them together inside the word error rate algorithm that is implemented inside the accuracy framework that we just covered. And then it dequeues the request from Luigi and marks it as complete. So this project has a few impacts, primarily that there's going to be an economic benefit here. The speech recognition industry is rapidly growing due to recent events and also to the increased efficiency of open source speech recognition models and new algorithms and computing power continuing to advance. There are estimates that the industry could be worth more than $30 billion by 2025, and it's currently worth $9.12 billion, according to some experts. There's also some societal benefit that it's, of course, easier for students. And as Manal mentioned at the start, the EVT service is considered very useful by most people who actually use it. And globally, an international audience often finds it easier to understand written text than spoken words. So that is another benefit. There's also some issues that could possibly be present. The algorithm might be trained to not work as well with certain accents, which could lead to the sort of implicit discrimination where people would value one lecturer's lectures less because the transcription doesn't work as well as someone whose accent corresponds better with the algorithms. And then also, personal privacy could be an issue if you're gathering data from people's personal information when training your neural networks, which might be a problem because they require huge data sets. And so some of that could come from something that it probably shouldn't.
Okay, great.
Yeah, so these are the accomplishments we achieved over this quarter. We provide an efficient model of running and comparing different speech recognition softwares. And users don't need to worry about things like operating system, hardware, storage, audio conversions, etc. And we installed the training framework for training. And most importantly, the whole system can be accessed remotely. And this is our final deliverable list. The only thing we weren't able to finish is the domain-specific model because the training was very time-consuming, and the server crashed once that we couldn't restore the checkpoint data. But our mentor said it's not necessary to restart the training because there are many other open source models ready to be used. So other than this, we established the accuracy testing framework. We made the whole system ready to be remote accessed, and we implemented the comparison and storage of transcripts. So that's the end of our presentation. Thank you.
Thank you, Team E. Any questions for Team E? This project is very relevant to our current situation since many of the lectures are delivered online.
Family has always been central to Rockabama's life. You could see that he didn't uproot his whole family to
Any questions from the audience?
in Chicago, and he would regularly commute back and forth to ensure that he.
One question, can you clarify again what is the Luigi used? Where is the Luigi used in your final deliverables?
Its functions sort of as a wrapper around the accuracy framework. It's like it's sort of like a platform that makes it so that one server doesn't have to handle potentially like 10,000 requests at once. It would sort of distribute the load.
Mhm. So in your final report, are you going to show this benefit of Luigi?
I suppose we should. Yeah.
Do you have a plan? How are you going to demonstrate this?
I think it's going to be difficult to directly demonstrate it because this is something that we could only show that if there are actually a lot of inputs being sent to the server and then the server is more efficiently able to handle it, then it could be more of a improvement or a more of a efficient use of the server. So we have to look into doing that. But other than that, if like only like 1 or 2 inputs are being sent to the server, then it's not really that much of a benefit.
Okay. Okay. Any other questions? Okay, if not, we will conclude our final presentation here. Thank you everyone for attending this, especially thank you for all the mentors for supervising our student teams across this entire quarter. For the student teams,
and from August to
remember
December
to submit
2020, we'll be
your
expanding.
final report by Wednesday, and also send the deliverables to your mentors as well. Good luck with the rest of the quarter, and stay safe in the summer. Thank you, everyone. Bye.